Today, I want to start off with a few observations about your quiz submissions. These are just things that happened a lot on the quizzes, and so it was worth taking some time today and talk about why I said those things. Because usually I'll make a quick note on your quiz and then just kind of move on because there's lots of quiz. So I can't write detailed explanations. It's also this little text box. It's hard to write detailed explanations. First thing I want to hit is that a row of zeros means nothing for the solution set. So we can't say that there's an infinite number of solutions because there's a row of zeros in the augmented matrix. A row of zeros in the augmented matrix means nothing for the solution set. You can never explain a solution set and bring up a row of zeros. So pretty much don't bring up a row of zeros. Take a look at this, this augmented matrix. The top two rows might look familiar to you. But I've added this third row, and here's the reduced echelon form of the matrix, 1, 0, 2, 0, 1, 1, 0, 0, 0. This last row does in fact mean 0 is equal to 0, but that doesn't mean anything. Notice that each column in the coefficients matrix is a pivot column. We've got a pivot in the first row, first column, and the second row, second column. No free variables. No free variables in the corresponding linear system. So notice that this matrix does not have any free variables because this matrix does not have any variables at all. Variables are something that happen in equations, not matrices. So we have x1 is equal to this reduced echelon form would correspond to x1 equals 2 and x2 equals 1. Or in parametric vector form, just the vector 2, 1. So we have a row of zeros. That means nothing for the solution set. Sometimes there's a row of zeros and there's infinitely many solutions. Sometimes there's a row of zeros and there's exactly one solution. Sometimes we can have a row of zeros and still have an inconsistent system. So a row of zeros means nothing for the solution set. So don't use row of zeros to justify anything. Notice that the corresponding linear system here, the corresponding linear system would be x1, because this is an augmented matrix, minus x2 is equal to 1, 3x1 plus 2x2 is equal to 8, and 4x1 plus x2 is equal to 9. So you could probably see how I generated this third row. I just added the first two rows because I wanted a row to disappear. Mechanically, what the reduced echelon form would look like is just x1 is equal to 2, x2 is equal to 1, and 0 is equal to 0. And we just usually don't write that part. What we're looking at here, is three lines in two-dimensional space that intersect in a single point. So let's see, where's my Desmos? Oops. There. Now let me try this. Okay, it's not gonna let me do that. How about this then? Apparently I have too many windows. So here we're looking at x minus y equals 1 and 3x plus 2y is equal to 8. And we see the intersection of 2, 1 like we saw last week. That was the first example. If I throw in the 4x plus y equals 9, we're just dealing with a third line and all three lines intersect at a point. The row of zeros meant nothing. Any questions? So that's the first thing that I wanted to point out. So a row of zeros means nothing for the solution set. Some minor things that I wanted to point out, some kind of form things. Notice that I didn't write anything in between the matrix, the original augmented matrix, and the reduced echelon form. In particular, we did not want to put an equal sign in between our steps. A lot of us come from traditions where we just stick equal signs in between all of our steps, and we have to stop doing that. You can't just put equal signs in between all of your steps because those things might not be equal. So don't put, the two matrices are not equal, they are row equivalent. So don't write anything in between. Just leave space. What I mean is no equal sign. The matrices are row equivalent, not equal. The matrices are not equal. They are row equivalent. So they're not equal matrices, they're row equivalent matrices. They have they correspond to linear systems with the same solution set, but that does not make the matrices themselves equal. So another thing that I wanted to point out is that we have two forms of solutions to linear systems, vector equations, and matrix equations. The general solution and the parametric vector form. So when we just list what x1, x2, x3, x4 equal, going down the list, that's the general solution. In the general solution, you just want to list all of the variables. So in the general solution, we just want to list the variables. In parametric vector form, we want to write the general solution into vectors. So parametric vector form, that's when your solution looks like a vector. In this case, we don't have a parameter because we had a unique solution. But in parametric vector form, you just gather up the variable, the list of the variables, x1, x2, x3, x4, and then separate them out into individual vectors. Hard to see in this one because we had a unique solution, but that's that. So those are some of that's the first thing I want to point out. A row of zeros means nothing for the solution set. Don't put an equal sign in between matrices that are not equal. Also, we would not want to put an equal sign between, say, this matrix and this solution to the corresponding linear system, because a matrix cannot equal something that is not a matrix, like a general solution or parametric vector form. All right, another thing to note. This solution is the solution to the corresponding linear system, not the augmented matrix. The matrix does not have a solution. The corresponding system or equation has a solution. So these are the solutions of a system, not the matrix. You wouldn't want to say something like the matrix, X is the solution to the matrix. That doesn't mean anything. A matrix does not have a solution. An equation has a solution. So these are solutions to the corresponding linear system. So it's not solutions to the matrix. That doesn't make any sense at all. I'd like to play tennis, but I don't know how to hold the bat. There's no bat in tennis. That doesn't make any sense. So also notice that we have variables x1 and x2. The variables do not belong to the matrix. The variables belong to the system or the equation. So these variables x1 and x2, a matrix does not have variables. So another thing to note, a matrix does not have variables. Variables are a thing that we find in equations and systems. A matrix does not have variables. So you wouldn't want to say that the matrix has a free variable. That doesn't make any sense at all. A matrix does not have a free variable because a matrix does not have variables at all. Equations have variables. The solution set to a linear system or an equation could have free variables. A matrix does not have variables. Systems or equations it's a system or an equation that has variables. When we want to talk about basic and free variables, those are part of the solution set. Solution sets to systems or equations have basic or free variables. If you said the system has some free variables, then that's fine. That implies that we're talking about the solution set to the system. But the point that I want to make here is we would not want to say that the matrix has a free variable. That doesn't make any sense at all. The matrix doesn't have any variables at all. The whole point of the matrix is to stop writing all the variables. It's to get rid of all that bookkeeping. If you say the matrix has free variables, you're getting your point across, but you're making your point very badly. You're trying to play tennis, but you don't know how to hold the bat. That's not how, those things don't go together. So first thing that I wanted to point out, along with these other kind of minor points about the language, and this is just the language that we're getting used to, is that a row of zeros means nothing for the solution set. If you type out because a row of zeros, stop, go back, and delete that because it doesn't mean nothing. Number two, we only care about the rightmost column of an augmented matrix. We only care about the rightmost column of an augmented matrix. We only care about the rightmost column of an augmented matrix. So if you invoke rightmost column, you've got to say afterwards of the augmented matrix. So for example, let's suppose that we have a linear system that says x1 minus x2 is equal to 1, 3x1 plus 2x2 is equal to 8. That has a solution, but this one does not. So let's suppose that we're tasked with solving this linear system. We would write the augmented matrix 1, 3, 4, negative 1, 2, 1, 1, 8, 7, and find its reduced to echelon form, which would be 1, 0, 0, 0, 1, 0, 0, 0, 1. So we have a pivot in the first row, first column, second row, second column, third row, third column. More importantly, this is the augmented matrix. of a linear system. So we can say, since there is a pivot in the rightmost column of the augmented matrix, the corresponding system is inconsistent. There is a pivot in the rightmost column of the augmented matrix. We can't just say there's a pivot in the rightmost column. Because we're all new at this, you have to tell me that you understand that rightmost column we only care about in an augmented matrix. So you have to write, there's a pivot in the rightmost column of the augmented matrix. Therefore, the corresponding linear system is inconsistent. Two things going on here. First of all, if you invoke the rightmost column, you have to say of the augmented matrix, because that's the only time we care about the rightmost column, and specifically calling it out as a rightmost column. The second thing that we want to point out is that it's the linear system that's inconsistent, not the matrix. A matrix cannot be consistent or inconsistent. A matrix is not an equation. It's not the matrix that's inconsistent. That doesn't make any sense. It's the linear system that's inconsistent, not the matrix.
So should we just think of the matrix as like a method of solving it, but not like it's like not an indicator of anything, except like unless we like translate it back to like the what's it called, the
Yes.
solution sort of, or like the
Yes.
equation.
Yes, we could think of the augmented matrix as the augmented matrix is the tool that we're going to use to make draw conclusions about either a linear system or an equation, or we'll use it to determine dependence or independence of a set of vectors. So it's just a tool that we're using. It's not
Okay.
what we're making we're not making conclusions about the matrix.
Okay.
Technically, we are in the beginning, because we're still learning about matrices. We want to see what these matrices tell us. But we want to be very specific with our language so we don't get confused later on. Spend some more confusion points now so that we don't acquire more confusion points later. So two things. Rightmost column of the augmented matrix. So never write rightmost column without following up with of the augmented matrix. And make sure that when you're talking about inconsistent, you're referring to a system or an equation. That's what gets to be consistent or inconsistent, not a matrix. The matrix is inconsistent means we're trying to play tennis with a baseball bat. Any questions?
I have a question from the first part that you explained. For a parametric vector form,
Yes.
I remember in our last session, you wrote something like x equals, and then you put the first column like 1 and 0, just the first two, and plus x2 times 0 and 1, and you didn't write like 2 and 1. So I just want to know that if we write it like that form, it's going to be the same as x equals 2, 1.
Yeah, we don't want to, I don't know what I was writing when I broke it out into as a linear combination of 1, 0 and 0, 1. That must have been something else. So that's actually our third thing that we want to talk about, going from the general solution to the parametric vector form. So let's talk about that.
Yeah, okay.
Let's go from general solution. So let's suppose that we have a general solution. Let's suppose that x1 is 5 minus 3x3, and x2 is negative 1 plus 4x3, and x3 is free. Remember, in the beginning, we're going to label our free variables as free variables. Notice that when I write my general solution, I just list the variables in order, x1, x2, x3, and so on. There's no reason that the free variables have to be at the bottom, just list them in order. So when we're talking about general solution, list all the variables in order and make sure to label your free variables. When you write x1 is equal to 5 minus 3x3, you are implying that x3 is a free variable. But I need you to explicitly state that x3 is a free variable because we're new at writing general solutions. I want you to know that x3 is a free variable. I want to know that you know that x3 is a free variable. The reason that I want to do this is that sometimes in one of the problems, say if x2 is a free variable, you write x1 in terms of x2, but some of you, a lot of you actually, wrote x2 in terms of x1, and that's not how it works. So you're not understanding what a free variable, the free variables and the basic variables. So make sure you label your free variables. Remember, basic variables correspond to pivot columns. Free variables correspond to non-pivot columns. I said that backwards. Pivot columns correspond to basic variables. Non-pivot columns correspond to free variables. So one of the things that we did, and this is the way we want to label our free variables. x3 is free, with just the words is free. x3 is free. So one of the things that I wrote last time is the way we're thinking about these things. What we want to do is summarize our general solution into parametric vector form, but we need to separate them out. So there's some stuff that goes on in the middle. So I want to summarize into parametric vector form which means I'm just going to take the general solution and make a vector out of it. But then I'm going to want to separate out a fixed vector and then the variable vector. So if we think about what x1 is equal to, or if we just write down what x1 is equal to, x1 is 5 minus 3x3. x2 is negative 1 plus 4x3. And what I did a poor job of explaining last time is this x3 is free. How does that show up in the parametric vector form? So the way we're thinking about it, the way we imagine x3 is free, we're just saying x3 is 0 constants plus 1 copy of x3. This is not how we would indicate a free variable. This is just us thinking about what it means for x3 to be free and how we could fill that in so that we can fill out the parametric vector form. So this is not something that we would want to write. So some of you, a lot of you, in fact, wrote x2 equals x2 to indicate your free variables. And that's not what we want to do. We just want to write x3 is free. This is just how, when I wrote this is just how we think about it. This is just us thinking about what this means. I wrote us very small because this is a big idea. So when we think about x3 is free as being 0, no constant, plus 1 copy of x3, now we can separate out our parametric vector form. Our constant vector is going to be 5, negative 1, 0. That's the y, in y equals mx plus b, that's the b. And then we're going to separate out a vector that's the multiple of x3. And that's going to be -3, 4, and 1. And so here's our parametric vector form.
So I mean that, can we do this one for the set of solution that doesn't have the free variable?
Yes. In that case, if we don't have any free variables, then we just write the vector without them. So if we didn't have this x3, we would just write the parametric vector form is 5, -1, 0. That's what happened in our first example. Or rewind a sec. We had a unique solution, no free variables. X1 is 2, x2 is 1. The parametric vector form is just going to be this one vector. No parameter because there was no free variable. So just list it as 2, 1. So we want to list just list all the variables in order, x1, x2, x3, however many there are. I think on the next homework one goes out to like x50, and I'm just kidding. It doesn't go that far, but it could. And we want to label our free variables. Also, we want to remember that pivot columns correspond to basic variables. Pivot columns in the augmented matrix correspond to basic variables, and non-pivot columns correspond to free variables. I recognize that my grading style is very frustrating because some of you just either left off your free variables and I gave you 0 points and made you do the problem over again. And all you had to do is take your other one, your previous wrong answer, and add the line x3 is free, and then full marks. I know it seems harsh to take off all the points, but since I'm letting you redo the problems, there's nothing wrong with taking off all the points for a problem, because you can redo the problem and get full credit for it. So I'm not going to do any kind of partial credit. So I just decided to make my life easier by taking off all the points for a problem for any little tiny thing that's gone wrong, and letting you do the problem over again for full credit. Once again, going back to the original principle, I want to set up a system where it encourages you to do work and fix your mistakes rather than stops you from doing that. So that's what I wanted to talk about with regards to parametric vector form. I talked about that the sets of vectors do not have variables, equations have variables. Oh, I talked about matrices do not have variables. So one distinction I want to make sure that we point out is that we can have a set of vectors versus a matrix versus a system. There's a lot of overlapping language that we have in linear algebra. If you think about Calc 2, when you're doing sequences, series, and power series, there's a lot of times that we write the limit as n goes to infinity. But whether we're doing a ratio test or limit comparison test or just a test for divergence, the conclusion is always different. So there's different words that go with different things. So a set of vectors would just say, maybe have a name, S equals V1, V2, and V3. A set of vectors is just a collection of vectors. It doesn't have rows and columns. It just has vectors. It doesn't have no rows and columns, no pivots. It's just a set. So no rows and columns. So no rows and columns. Since there's no rows and columns, there's no pivots. No variables, no solutions. It's just a set of vectors. It doesn't have any of those elements. It's just a set of vectors. It can be dependent or independent. So it is something that we could describe with dependence or independence. So a set of vectors can be dependent or independent. This is different than a matrix, even though the columns of a matrix can be considered, can be thought of as a set of vectors. So a set of a matrix here I just listed this matrix with the names of the columns, A1, A2, and A3. So notice the difference in notation. I put it in square brackets like we do for a matrix, but I did not separate the columns with commas because I'm not making a list. I'm writing the columns of a matrix, and we don't put commas in between the columns of a matrix. So a matrix has rows and columns, so it has pivots. It has rows and columns. It has pivots. It does not have variables or solutions. I switched my colors around. Oh, now it's bugging me. Now it's bugging me. So I have recorded evidence of the things that bug me. So a matrix has pivots, has rows and columns, so it can have pivots. So it has rows and columns. And so it has pivots. But like we said earlier, it does not have variables. We can put a matrix into an equation, then we're talking about, but then we're in the next column, systems and equations. So a matrix does not have variables, and so a matrix does not have solutions, no variables and no solutions. We wouldn't want to say the matrix is dependent or independent, but we can think of the columns of a matrix as a set of vectors. So the columns of the matrix forms a set of vectors. So we wouldn't want to say that the matrix is dependent or independent, but we could say that the columns of the matrix can be dependent or independent. So we wouldn't want to say that the matrix is independent. What we're trying to say is that the columns of the matrix can be dependent or independent, because we could think of the columns of the matrix as a set of vectors. Exciting day when we have the naming of parts and how the words go together. But one of the reasons that we have to do this is that math is a very precise language, and we want to make sure that we're not trying to play tennis with a baseball bat. Although now that I think about it, there's a VR game where when you're playing tennis, you could randomly change your racket into a baseball bat or a pool cue, or it's just a weird game. A system or an equation that does not have rows or columns, does not have pivots. It does have variables and it does have solutions. So a system or equation does not have rows and pivots or rows and columns. No pivots in the equation, but it does have variables, and so it does have solutions. If we're using the word solve, we must be trying to find the solution set to a system or equation. You would also not want to say that you're solving a matrix. That doesn't make any sense. Solve is a word that we specifically want to apply to equations. Solve has a more general use. People will put up an order of operations problem on social media and say, can you solve this? And if you want to be super pedantic, be like, oh, well, it's not an equation, so no, I could simplify it for you. But then you're being super pedantic and someone should call you on that. Someone should be like, oh, dude, why are you being so pedantic? You know what I meant. You know what I mean? It's like when you ask the teacher, can I go to the restroom? And the teacher says, I don't know, can you? And you say, look, moron, you know what I meant. You understand how language works. You knew what I meant. That was an unnecessary correction. Right now, you're thinking all the corrections that I'm throwing at you are unnecessary, but I assure you they're vital to the survival of the species. I'm just kidding. It's not that critical. It just sounds weird. I see a raised hand. Do you have a question?
Yes, I do. I was about to ask if you can think of a matrix as, I guess, representing a system in terms of column vectors. That's what I was thinking about with the matrix. And when you perform row operations on a matrix, whatever you get in REF, you can correspond that to solutions of, whatever linear system you're working with. Is that right?
That is absolutely correct. We're
Okay,
using a matrix to represent a system, and you find the reduced echelon form, and you think about that. That'll give you information about the corresponding solution set. The solution set is connected to the system. So what we're doing is we're looking at a system, we're translating that into the matrix, we find the reduced echelon form, that's where the operations happen, and then we translate that back into the solution set to the original system. So yes, that's a good way to think about it. Any other questions on language? We're going to have lots of discussions on language. They won't be as extensive as this one. And there are a lot of times that you're going to write something on your quiz in your explanation, and I'm going to throw a correction your way, and you're going to think this seems like it seems like you're being very picky. When it seems like I'm being very picky about your language, that's only because I'm being very picky about your language. We're trying to do, we're trying to speak math properly, and so we want to make sure that we can talk the talk. The last thing I want to talk about as far as going over these things is linear independence, which is, and I want to talk about it in more detail. So I'm going to pause this video, and then we'll come back, and the next video will be about linear independence. All right, let's pause the video here, take a quick breather, and come back and talk about linear independence.